SwayamPrabha. Digital India. Educated India.
Okay, students, we have been continuing our discussion on the interfaces, and I am going to wind up today with few examples of different kind of interfaces. The last thing which I started in the discussion in the previous class was coincident side boundaries. As you know, I have shown you that it is possible to have some lattice points of both the crystals in interface type interfaces to match, if not all of them. And one such concept is coincident side boundaries. To give you an example that I started in the last class, here I am showing you two nets, one corresponding to the small white circles, you see here these are the small white circles, other one corresponding to the black dots. Now, it is possible to align these two nets falling on each other by giving a rotation around certain axis, and this big white blobs actually corresponding to this coincidence lattice, you see here these are the white blobs. So, finally, it is possible to generate or make two lattices, some points of lattices fall on each other by rotation of the net B with respect to the net A by 21.8 degrees Celsius. That is about 22 degrees Celsius by 111 axis of the net A. So, this is what is known as coincident lattice. That means, what we are basically doing here is that if I have two different crystals side by side, we can have the bonds formed between the atoms of the two crystals by rotating the one of the lattice with respect to the major axis of crystals by certain amount, by certain degrees of rotation. In fact, this rotation is basically done to coincide these points or the atoms sitting on each other, so that they can form bonds, but not all the atoms actually. It is only for certain number of atoms this kind of coincidence is possible. Obviously, if all the atoms are actually falling on each other, this will be a complete coherence interface, or even some atoms are falling on each other and some dislocations will be semi-coherent type of interface. But we can actually generate basically semi-coherent type of interfaces, which is not exactly semi-coherent, but partially semi-coherent type of interfaces by doing such a kind of simple rotation of the crystal lattices. So, in this regard actually there are few things which was governed in the literature, and one of the important thing of coincident lattices is the fraction of atoms in coincidence at the boundary is always known as the density of the coincident sites, correct. Basically, all the atoms are not actually coincidence with each other along the boundary. So, therefore, we have to consider the important factor, that is the fraction of atoms which will be coinciding with each other on the boundary. In fact, we do not take into that consideration, we take into consideration reciprocal of the density, and reciprocal of the density is usually considered as a parameter to describe the coincident sites boundary, and the reciprocal is basically designated by a letter called Greek letter called given here like this is summation. Okay. Now, that basically tells you how many of lattices are actually falling on each other. In this regard, one of my teacher has actually extensively worked on in his young days, and he gave few relationships which are valid. This can be obtained, in fact, it is given in the books how this can be obtained. The relationships are not very difficult. Not only could the rotational symmetries operations which we have done in the last slides can bring back the lattice with some kind of a self coincidence, but partial self coordinates also can be attained with specific rotations along the about other axis. Okay. That is what I have been telling about it. Partial coincidence is always possible. These lateral rotations are not only able to produce coincident side nets at a boundary between two crystals, but also they are capable of yielding concept of coinciding side 3-dimensional lattice. Obviously, in 3D, if these points are matching, some of them, not all of them or fractions of them, then we can call them as a different type of 3-dimensional coincident side lattice. So, there are 4 factors which are responsible for making these coincidence possible. One is the obviously the rotation axis along which we are rotating the one crystal lattice as per other. Second one is the angle that I have already discussed. Third one is the coincident net on the plane HKL normal to the axis. It is obvious, because if I have a 1 1 1 axis, whether the coincidence plane is 1 1 1 or some other plane, that will dictate what kind of things. And obviously, the important parameter which I have just now told you is the rotational reciprocal of the density. That is the important aspects. So, in fact, all these 4 parameters are not independent. Mathematically, it can be shown that all these 4 parameters are related. Suppose if I define the coordinates of a coincident lattice in HKL plane, any coordinate of a point and the HKL plane as a n is h square plus k cross by L square, then sigma, sorry, not sigma, this is one kind of a summation term is equal to x square plus y square n, and angle is 2 root n tan inverse y by x. So, therefore, we can actually relate, you can see that if I know n can be easily related, because n is nothing but the plane or the directions in a cubic lattice, they are similar, same, and x and y is basically your coordinates on which this coincident lattice will happen, they are related to each other. So, by doing by using these relationships, we can actually generate different kind of sigma boundaries. Okay. Different kind of boundaries, sigma 9, sigma 27 or sigma, even other boundaries are also possible to be generated. Sigma these boundaries which are where the coincidence thing happens is basically some of them are twin boundaries nowadays called. Fine, example of a twist boundary. So, let us give me an example of relationship, how the relationship can be used. First, let us look at the right side. If I consider simple cubic structure and consider one OO plane, and axis is perpendicular to that is 1 0 0 plane, 1 0 0 axis, and x and y obviously will be x axis and z axis here, that is 0 1 0, y axis and z axis, okay, they are given a little bit different way. You can actually define x and y depending on your uses, but there has to be perpendicular to the plane 1 0 0, okay, that is what is 0 1 0 and 0 0 1, that must be perpendicular to this plane. Now, n square is nothing but a square plus k square per L square, that is equal to 1. And suppose x and y is 2, 1, that is the coincidence point, coordinate of the coincidence point. So, therefore, sigma is basically 5 and theta is basically 53.1. So, if I rotate 53.1 degree one of the net with respect to the other, then I will get a sigma 5 boundary, that is what it says, if it is a simple cubic structure. Okay, so that is the known a rotation of 53.1 degrees about 1 0 0 axis of a simple cubic lattice gives the coincident side boundary of sigma 5. These sides also form a lattice with its unit cell whose sides are equal to root 5a or the boundary. Okay, the cell size of a reciprocal lattice is just 5 times larger than the primitive lattice. Let us see here, net A is basically small white dots, you see here small white dots, and net B is small black dots. And now the net B is rotated with respect to net A by 53.1 degrees, therefore, they come in coincidence with each other, some of them points, and this gives you these the white big blobs where the coincidence has happened. You can clearly see this was the unit cell of A atom and this was the unit cell of B atoms, okay, the black ones. So, compared to that, unit cell of these new is root 5 times bigger. Okay, that is what is happened. That can be calculated easily, because as you know this distance I know. So, therefore, we can calculate this distance I know, we can easily calculate the values of that. Anyway, we can actually generate different kinds of boundaries by using such as say this formulae, and this is widely used in the literature now. Okay, so this is basically a special boundary. Let me tell you, these boundaries do not exist in all crystals. So, therefore, these boundaries are very special and they can be actually generated by using different options in the crystal structure. Okay, now another one, this is actually of another twist boundary where again the plane is same, and no, this is exactly same, no, this is different. Okay, so if plane is same, rotation axis is 1 0 0, and if suppose coincidence point coordinate of this 3 comma 1, then what happen? This which becomes sigma become 10. Okay. In fact, 10 and 5 they are not much difference. It is only actually the lattice parameter will be divided, the points will be divided by number of points will be less in 5 by half the coincident points, and angle of rotation here will be exactly 36.9 degrees. So, if I actually rotate 36.9 degrees of the QJ axis, we can also generate a sigma phi boundary where the coincidence points will be similar to that what I have shown you. In this case also it is easily seen 36.8 is what is the rotation axis required in a cubic crystals to do that. And here you see the unit cell things are shown, it is root 5a is the distance of the new lattice parameter. Fine. So, actually in this way we can actually make tilt boundaries or twist boundary depending on that. You can see here it is much clear here, much clear here. If I have two lattices, one shown there, one shown the top A and B type, and you want to have a coincidence of the atoms, we can tilt so A, or actually here a tilt A here with respect to B with respect to this axis by 53.1 degrees Celsius. Then these are the points on which the lattice of A will be falling on lattice of points of B, other points it will not fall. So, therefore, there will be fraction of slides on which sides in the lattice of A, lattice of B actually will be forming bonds with the atoms of A, other sides it is not form bond, they will remain dangling or they will be unsatisfied. So, by that way we can actually create a simple tilt boundary which is known as coincidence sign tilt boundary. Again same thing has shown, it is a much detailed way how the coincidence sides forms. You can actually rotate 36.9 degrees and create another type of sigma phi boundary, tilt boundary. 36 of 5 will lead to at angular, you can see here these points are at an angular angle with respect to the B lattice, not exactly falling on the B lattice, right, in the case of in the first case where the rotation was 53.1 degrees Celsius. Last one, I would like to say you that if one considers atoms as touching sphere, the illustrated boundaries should contain only pair of overlapping atoms just to the rights of the each coincident lies sides on these boundaries. And the problem of this overlap could be relieved by removing one atom from each of these pairs by relative translation of the lattice above the or below the given boundaries. Okay, that is what is shown here. We can actually, instead of coincidence, these are actually sitting on each other. So, instead of coincidence we can actually move these points, this one here or this one there like that way, or this one there or this one here, and create a boundary, that is also possible. So, there are many such options exist. Okay, you need not go into details of that. If you are really interested to create such a kind of boundaries, you can look at these atomic constructions along 100, this is along 100 on a simple cubic, and do these kinds of different options can be generated, and these are all done actually in the literature. Okay, so now after discussing about different boundaries, let me tell you that these boundaries actually dictate the interfacial energies. What type of boundary, whether it is a coherent, incoherent, semi-coherent, special semi-coherent boundary, or it depends, it dictates actually interfacial energy. So, by interfacial energy dictates the shapes of the second phase. Okay. Now, in a fully coherent precipitates, what will happen? This is what is shown here. You see here these white atoms are actually the atoms of the matrix, and the black atom actually atoms of a precipitate phase, let us suppose. And the way they are forming that, there is an exact coincidence of the points or the atoms sitting on each other. Okay, and not only that, it seems that the interplanar spacing of the black atoms is same as that of the white atoms. So, because of that, the interface created by this kind of matching is basically coherent, fully coherent precipitates. And if you know, if the precipitate has the same crystal structure and similar lattice parameter, that can happen. Okay, and that means what? Energetically, all the surfaces, the precipitate and the matrix have a coherent interface, and they have a very specific orientation relationships. Crystallographic planes has to match on each other, each of these precipitate and the matrix. Situation happens in real situation actually happen in case of aluminum copper alloys or aluminum I think silver, aluminum silver alloys also, when the precipitates actually start to form at the beginning, and these actually known as, we will discuss in detail, known as Grenier piston zones or GP zones. GP zones actually are solute atoms sitting on a matrix surface, few layers of solute atoms. They have not yet formed the precipitates, which we will discuss in detailed manner when you talk about the second phase precipitates from the matrix. You see here, in that case, the shape of the precipitate can be anything. It basically it will be spherical, because there is no preferential interfacial energy change along any of the interfaces. So, this must be spherical precipitate. So, gamma plot of the alpha beta interface will be largely spherical, and equilibrium shape of a zone could be a sphere. Obviously, when we are doing that, we are assuming there is no coherency strain. What is the meaning of coherency strain? We are assuming that bonds actually are straight between A and B atoms, between the black and white atoms. That may not be the case, because atomic sizes of silver and aluminum may be different. So, therefore, the bonds may not be exactly straight when they are falling on each other. There will be little distortion, but while doing so, we are ignoring that coherency strain due to this distortion of the bonds, which are required to maintain the coherency across the interface. But still, normally we see these precipitates as spherical. We in the experiment also see. But when it is partially coherent, things do get changed completely. If it is partially coherent, that means some of the surfaces of the precipitates is coherent, and some of the surfaces are not coherent. Suppose you have a matrix and you have a precipitate which is like this. These are the surfaces which are coherent, and this surface is not partially coherent. The flat surface is perfectly coherent, but on the other hand, the curved surface is partially coherent. So, what will happen then? Normally, such a case, the gamma plot, the surface energy plot will be looks like a sphere with cusp. Okay, you see on the normal surfaces. That means along these surfaces, normal surfaces, flat surfaces, there will be cusps. Okay, sitting on that. That is what is shown here. This is spherical, and there is a minimum value on the flat surface. That is what is known as cusp. Now, the Wolff theorem predicts that equilibrium shape of these things will be a plate, or a disk rather, not a plate, with a thickness to diameter ratio given by the two interfacial energies. One is the gamma c, and gamma I, where this actually gamma c is basically semi-coherent surface precipitate, and other one is the incoherent interface gas energies. And precipitate shapes observed may deviate. They are normally this shaped, but it can deviate from this shaped a little bit because of two reasons. One is that in the above construction we have not considered misfit strain energy effects. Okay, because of misfit along these semi-coherent interfaces, there are dislocations, and this dislocation will lead to strain energy, which we have not considered. Second is that precipitate Wolff construction does not consider anything due to strain energy, it only considers the interfacial energy effects. Precipitate may not be able to reach the equilibrium state. In that case also, this may not have a disk shape. So, this precipitate may be much wider than the equilibrium shape if the incoherent energy edges grow faster than the coherent energy. That we will see in next few slides. So, finally, if one of the few of the surfaces are semi-coherent type and few are incoherent type, then you will have a disk shaped precipitator like this. This is just like a saucer on which we sometimes drink tea or coffee. You have seen that. Now, if it is completely incoherent, okay, you can see here there are all kinds of things are present here in this microstructure, which is basically precipitates of theta in aluminum copper alloy. Suppose it is completely incoherent, that means two phases have no complete different crystal structure, and they have no lattice matching. Okay. So, they are actually in random orientations. It is very unlikely that coherent or semi-coherent interfaces form and the precipitate is said to be completely incoherent. So, in such a case, the precipitate can have any shapes. Okay, it can have actually it says interfacial energy would be high for the for all the interfacial planes. The gamma plot and equilibrium inclusion shapes will be roughly spherical. It will be roughly spherical means it will not be exactly spherical, just like in case of coherent, but there will be distortion. The ones which is shown here is that, see, this is a plate shaped precipitates. You can see here this shaped. Okay, this is one is a they have a coherent interface here, but there is no coherency here. Okay. Similarly, there is a coherent here which is semi-coherent, semi-coherent here, incoherent there, and the one which is shown as a big one is basically has lost all kinds of semi-coherency, coherency. That is why the surface looks like a curved one. Similarly, here also you see here that the surface is slowly getting curved. So, that means the semi-coherency is getting lost. So, as the precipitates become bigger, the strain energy effects become stronger and they lose the semi-coherency or coherency with the matrix. So, in a normal picture, in a normal TM micrograph, if you look at all the aluminum copper precipitates, you can see all kinds of orientation relationships and different kinds of interfaces present on these kind of precipitates, which we will discuss in very detail when you talk about the precipitates. Well, just to give a better idea, suppose a precipitate may sit on a gain boundary, then what will happen? A precipitate sits on a gain boundary, the one which is shown here, you see here, there is a surface here, this is flat, but these two surfaces are actually curved, and this is a boundary, this is a boundary, this is a boundary. Okay. The 3 gains 1, 2, 3. Okay, 3 gains actually. So, this is sitting on a gain boundary, we are very sure. So, if that is what the case, then we need to consider what is the orientation relationships, or rather what kind of interface the precipitate is having with the different grains, 2 different grains. So, if is if it is completely incoherent with both the grains, then this is what it will look like. The precipitate will have such a kind of shapes. If it is semi-coherent on one grain, this is what it will be, incoherent in another grain. Okay. Similarly, here semi-coherent with one grain, semi-coherent with both the grains here, one part, and other part is incoherent with both the grains. All kinds of possibilities do exist. First 2 cases are very commonly encountered, the one which is shown here. This is basically in aluminum copper alloy precipitates. Here you see there is another one where it is a completely incoherent with both the interfaces, with both the grains, the precipitate phases. So, obviously, if it is coherent or semi-coherent along certain interface, the precipitate will like to keep that coherent incoherent interface intact, because that interface is the lowest energy interface or lower energy interface. So, precipitate will not grow along that, because if it grows and becomes bigger, there is a highly likely chance, or it is highly likely that this interface will lose the nature of coherency or semi-coherency. So, that is why precipitates always grow along the incoherent interfaces, where the energy is already very high. So, there is no loss of energy as far as the growth of the precipitate is concerned. This is normally seen in the aluminum copper precipitates. Well, just to give you some idea whatever time we have in this lecture, we have not considered mid-speed strain effect at all while talking about the last few examples, but what is its effects? Let me go back. Okay. When we have a suppose completely coherent precipitates fully and mid-speed is present, okay, mid-speed can be present in many ways. It can be present as a distortion of the bonds, or it can be present as a mid-speed dislocation also in case of semi-coherent interface. When mid-speed is present, formation of the coherent interfaces raises the free energy of the system because of the elastic strain energy effects. Obviously, bonds are distorted, right, across the interface. Because of that, there will be elastic strain energy, elastic energy will be high. So, no longer we can actually consider the equilibrium condition to be summation of Ai sigma I to be 0. Ai is surface area and sigma I is the energy of the system. We have to add with that thing delta Gs, which is nothing but a elastic strain energy, because strain energy will play a role. This is no longer cannot be ignored. And if the volume of the matrix which is shown here, suppose this is the volume of the matrix, in circle is cut out. If I take out the matrix, okay, matrix was there already, and these atoms I replace, okay, these atoms what are sitting I replace with the precipitate atoms, or some other atoms, smaller atoms suppose, then what will be? There will be negative dilation, negative expansion, okay, or that means the whole thing will shrink. It will shrink to a smaller size. That is what is called negative dilations. Okay, and this dilation train to inclusion with a smaller lattice parameter, that you can see, because we are putting smaller size atoms we have taken out these atoms on the matrix and put smaller size atoms. So, there will be dilation, there will be smaller lattice parameter of that, and this will so therefore, in order to produce a fully coherent precipitates, the matrix and the inclusion must be strained. That is what is shown here, because of the atomic sizes differences, in order to form the bonds between the precipitate and the matrix and keep the interface to be completely coherent. That means all the atoms bonds of the atoms are set to be satisfied, then the bonds has to be distorted between the smaller atom and the bigger atoms, that is between the precipitate and the matrix. And as you see, the unconstant misfit is basically A beta by minus A gamma A alpha, where beta is the precipitates and alpha is the matrix. Okay, R is basically A inclusion minus A matrix by A matrix. That is the way we define the misfit that we have already discussed. Now, if I look at it very carefully, what is this constant misfit epsilon which we are talking about? That is basically nothing but a strain. So, the stasis maintaining this coherency of the interface will distort the precipitate lattice. You can see here also that we clearly see that all the bonds are satisfied across the interface, but this is strained, the whole thing is a strain. You can see the region which is marked as a dotted line is strained. Now, in case of a spherical inclusions, which is the case here also, the distortion is purely hydrostatic. Why? Because there is no directional dependence of the distortions, it is uniform in all directions. So, therefore, we can actually get a lattice parameter of the new phase as related to epsilon by this parameter. Remember, epsilon is nothing but a misfit strain, the strain because of the change of these atomic sizes. If the elastic modulus of the matrix and the inclusions are same, which is not normally the case, it can be same in specific cases, and we assume that the Poisson ratio for the metals are basically 1 by 3, then this strain is basically 2 by 3 delta. Delta is what is known as misfit. So, therefore, misfit and misfit strain can be related the moment we know the elastic modulus of the matrix and these precipitates are same. So, when the precipitate is a very thin disk, what will happen? The in situ misfit is no longer equal in all directions, because it is a disk. Therefore, there will be some precipitates will be semi-coherent, some will be incoherent. As instead it is a large perpendicular to the disk, very large perpendicular to the disk, this is the disk. So, therefore, perpendicular to that is very large and is very small parallel to the disk. Okay. So, if it is this is the disk, this is the direction, it is very large, okay, and this is the direction parallel, this is the direction parallel, is very low. Okay. So, therefore, if I draw it again, this is the perpendicular direction where it is very large, and this is the parallel direction which is normally low. That is what you see here. This distortion along these lines are low than along these lines. That is what it says. That is what actually dictates the precipitate shapes to be it's a disk. So, therefore, we have to take into consideration these misfit strains if we want to really know the exact shapes. Well, one can actually calculate what is the delta G value in case of these misfits, and it is very clear the matrix is elastically isotropic. These are all very big assumptions, and therefore, precipitates in the matrix have equal elastic modulus. Then we can actually assume Poisson ratio to be 1 by 3, then delta Gs becomes 4 sigma epsilon delta square V, where basically this the mu is nothing but a shear modulus of the matrix, and delta I have already defined as misfit, and volume is basic V is the volume of the matrix, unconstant hole in the matrix. So, we can add up these things into this equation, and actually then minimize the whole equations and get these shapes of the precipitates. Obviously, Wolff construction will not do that, because Wolff construction does not take care the misfit strains, but one can actually do much better way now. Well, as you see here, misfit strain effects are very large. If I consider, suppose aluminum has a size of 1.43 Armstrong as the atomic size, and silver has 1.44. Therefore, the misfits zone misfit actually has a 0.7%. This is very small, but it is positive. But zinc on the other hand, it is a minus 3.5. Copper is all very large, it is almost it is 10% minus. Therefore, the shapes will be spherical in case of aluminum, silver. It will be also spherical in zinc, but it is because it is can be created can be accommodated. 3.5% is not very large, but the moment it's become copper is very large, it will be a dissipate. So, whenever the delta is less than 5, strain energy effects are less important than the interfacial energy, and therefore spherical zone forms. But when it is more than 5, then only interfacial energies has to be augmented with the or added with the strain energy effects and calculate these effects. Okay, let me stop here, and so therefore, you see that these interfaces do play a very important role. In the next class, I will show you simple thermodynamic analysis, how we can actually use these concepts to explain different phenomena in the phase transformations.